engage with nuclear fusion in it. So aজকে we'll be starting the radioactive decay, but we need to go through the fusion and fission. Fusion and fission is not directly provided in your syllabus, but I think we need to just roughly go through it. Directly provided, the process is not there. They just talk about fission and fusion generally. Okay, I'll explain. Don't worry. So.
Recording in progress.
Okay, set to screen. Last class we saw that, or multiple classes so far, we saw that when elements are below iron in the graph of energy or proton number, this is, by the way, binding energy per nucleon. So you have this binding energy per nucleon graph here, and the peak of the graph belongs to which element? We have gone through this multiple times, iron, right? So this is where iron is, and elements that lie here, these elements, these will want to become iron, and those will also want to become iron, all these elements out there. Now, there are two ways in which you can become iron. One is through something called radioactive decay. It's like a half-life where decay kore hoy. Arta hocche a shortcut where the conditions are right, an element will go from a lower state to a higher state directly. So oi process is called nuclear fusion, and we have different types of fusion out there, but our syllabus deals with only the hydrogen one. So hydrogen that only explain korbo. And when it comes to larger elements, heavier elements, they want to break down, and they want to form what? Iron, right? So the one will be following here. By the way, this is called nuclear fission, FISSION, and this is uranium, and hydrogen. So how can uranium become more stable by the process of fission, and how can hydrogen become more stable by fusion, right? Now, the term nuclear fusion, you have learned this in your O levels. O levels say GC te bhaloi chilo, IGC te ekটু কম ছিল. Can anyone tell me what is the process of nuclear fusion for 1 mark? The most elementary answer. Right. Two nuclei fuse together, merge together to form what? A heavier, more stable nucleus. Okay. And what was fission? FISSION, fission. Yeah, it was a splitting process that resulted in smaller, much more stable nuclei, right? So, actually, the korbo is I will show you the actual process that takes place in a star. Bear in mind that this is actually not mentioned in the syllabus. Okay, it's something that I think should be useful, because the question koreba. Not that they'll ask you to describe the process, they'll ask you to find the energy. And I'm last class math course. Remember we did this one, two helium joined together to form a helium. So that's why I want to go through this. So let's try to understand how to make two hydrogen nuclei merge together and form helium. What is the requirement? So that they can ask you. Okay. So these two are smaller particles, hydrogen here, and for them to form your helium is actually a multi-step process. Step number one is that the hydrogen here, which is a nucleus, is positively charged, and the hydrogen there, which is also a nucleus, is positively charged. And I think you should know that these are basically protons, deuteroproton, and the protons are coming towards each other. Plus and plus, what will they do to each other? Repel, right? So what will happen is this will repel that, that will repel that. So you need to make sure that your particles have enough energy to overcome the what? Repulsion, and come and collide, which is actually not very easy. Typically, let's say I fire a proton towards a proton, right? Typically, what would happen? If you fire a proton towards a proton, yeah, you'll find that as the positive particle is moving towards the positive particle, there's repulsion out there and it slows down. Because repulsion, and they better slow most of the time it slows down and what? Stops. And then what does it do? It goes the other way, right? But for fusion to take place, you have to ensure the particles go so fast they can overcome the repulsion, they can collide hard enough so their quarks become one. That's what we want, right? Now, unfortunately, it requires a lot of energy, and the temperature that allows you to achieve this is what's the barrier for fusion. Okay, so temperature for fusion to take place is 1 into 10 to the power 7 Kelvin, and this is minimum. Higher will are better, but this is the minimum energy needed. So that's like 10 million degrees Celsius. Okay, 10 million degrees Celsius provide korle particles will have enough Ke that they can overcome the repulsion and merge and become one. Because আমার কিন্তু requirement not to just overcome repulsion, not like come here and stop. I need to overcome repulsion and go so far and close that the what inside become one, the quarks. So quarks will merge korbe. Also, another requirement, this is actually more important. You need to have very high density. So density is actually a higher requirement than pressure. Can I believe? So imagine a room there are 2 protons right now. Probably there are. And they have enough energy to fuse. Somehow they can, because energy distribution is random. There are molecules in this room that have energies more than the surface of our sun. And a room there is probably a molecule lying around somewhere whose energy is close to absolute zero. It is what it is. But average energy only high. That's why it's called average kinetic energy, right? So there are protons in this room right now. They're moving as fast as this. Let's say they collide, they fuse, and they become helium, right? Is that going to create a star in this room right now? Why not? Yeah, because only 2 of them did, and 2 of them won't start a star reaction process. You need to have how many of these collide? Lots of them. And for that to happen, you need to have lots of particles. And for that to happen, you need to have a what density? A very high density. So if you have very high density and high pressure, high temperature, there will be enough particles colliding. And every time they collide and fuse, what do is they release energy. And that energy is what fuels our stars, right? So this is nuclear fusion. Now, এটা করে যেটা হয় একটা myth bust করি আছে এখানে, because there's a confusion out there. Students think that in our sun, hydrogen and hydrogen fuse together and they form helium and they produce energy. That is not entirely true. That's partly true. এটা এখন দেখো কি হয়. So when a hydrogen and a hydrogen fuse together, they don't form helium right away. They form this. What is this? Deuterium. It's an isotope of hydrogen. Okay, so hydrogen fuses with hydrogen to form hydrogen. And a particle ko lagbe na tomoder A2 te, but it was in your AS. Can anyone recognize these particles? Yeah, it's a beta plus particle. Or it's a neutrino, right? This is an electron neutrino. Remember the leptons that we had? And beta plus is also commonly known as the positron. Okay, so positron plus electron neutrino. Anyways, deuterium is what we want. Okay, so deuterium যখন আবার হাইড্রোজেনের সাথে আবার ফিউজ করবে, that's the step that produces the energy in the sun. The famous step of hydrogen producing energy by fusion. This is that step. But this step doesn't happen all the time, because you need to have what for this step? Deuterium. So Earth fusioner হচ্ছে barrier is not the high temperature, high density. It's actually the what? Deuterium availability. So deuterium to produce korte parle, the process will be one step easier for us. Okay, so deuterium to available now, it's actually very rare. So এটা fusion করে produce করতে হয়. That's why ওটা production takes up most of the energy. Right? So this is what produces the energy. Now there's an interesting step here. The helium-3 will actually merge with another helium-3 to form helium-4. And helium-4 is more stable, in fact, most stable of the ones we have. And this also produces energy with the release of what? 2 hydrogen. Wasn't 2 hydrogen what started this all together? So this process kind of replenishes itself, feeds back the particle. So in theory, this should go on for what? Forever, right? But it doesn't though. Because at the math error, 1 hydrogen, 2 hydrogen, 3 hydrogen is needed to produce that. তার মানে এটার জন্য কয়টা হাইড্রোজেন লাগছিল আমার? 3. এটার জন্য কয়টা হাইড্রোজেন লাগছিল? 3. But what am I getting back? 2. So total 6 দেওয়া হচ্ছে আর 2 ফেরত পাচ্ছ. So yeah, so the process is trying to slow down the depletion of hydrogen, but hydrogen can deplete হতে থাকে. And this is one of the reasons why stars last so long, because ওদের সব হাইড্রোজেন রাইট অ্যাওয়ে চলে যাচ্ছে না, হাইড্রোজেন যাচ্ছে কিছু ব্যাক করে, যাচ্ছে কিছু ব্যাক করে. So that's why the store of hydrogen is going like that, not straight down like this. That's why stars last for so long. Okay, so yeah, this is the fusion process. তোমাদের এক্সামে সো ফার কি আসছে বলি, ম্যাথ আসছে উইথ লট অফ নাম্বারস, but theory wise এই জিনিসটা এখন জিজ্ঞেস করে না, the one that I've just described so far. I've given here this as a safety আর কিছু না। তোমাদের যেটা জিজ্ঞেস করে what's nuclear fusion, what's nuclear fusion? It's a process by which smaller, lighter nuclei merge together to form a heavy nucleus with the release of what? Energy. That's it. Okay, that's the thing that has shown up so far. Do you understand? Okay, so that's nuclear fusion. আমি ওটা definition দিয়ে দিচ্ছি। And next হচ্ছে fission. Fission is the one, the bigger one that becomes the smaller one, right? So fissionটা হচ্ছে is famous because fission currently তোমাদের O level syllabus I think তোমাদের মনে হয় ছিল, did you have the nuclear reactor in your O levels? Yeah, so in nuclear reactor যেহেতু আছে syllabus, it's like basically revision of that. So if you remember GC তে ছিল, IGCSE তে ছিল না, this is called a chain reaction. Chain reaction কখন হয়? So uranium 235 is unstable, but it doesn't undergo fission. কেন? বললাম না, the big elements want to become small, right? The nuclear fission হচ্ছে uranium 235 এ হওয়ার কথা, হয় না কেন? Equal number of আচ্ছা, okay, I'm বলি। So yeah, so 235 যে uraniumটা, it's actually unstable, but it is not over the tipping point. So there's a tipping point out there. Tipping point কি বলি, something is unstable and it wants to become stable. So there are two pathways out there. আমরা আজকে আরেকটা pathway start করব, but the two pathways মধ্যে one is the one that's a very slow, long process where the nucleus gradually, randomly releases particles and becomes stable. What is that called? Radioactive decay. The one you had in O levels, that larger particle will release like alpha particle, beta particle, gamma particle, and that also attains what eventually? Stability. But it's a what process? It's a slow, long process where it does become stable, but the need is not urgent. But 235 এর সাথে যদি আমরা এটাকে কিছু করে 236 করতে পারি uranium, it can't exist. 236 uranium এর the structure is so fragile, right? It can't exist for momentarily there. So somehow যদি 236 করে ফেলতে পারো, you take it over the tipping point. So what does it do? It just snaps and breaks right away. And that's when the fission process takes place. So uranium কে যদি ফিশনে এটা entice করতে চাও, what do you need to do first? Yeah, you need to make it 236. 236 এ কেমনে করা হয় কারো মনে আছে? Yeah, by introducing a slow moving neutron. যখন একটা slow moving neutron এসে 235 এর সাথে introduce হবে, the neutron gets absorbed, and what does it become? 236, and 236 is very unstable. Okay, and suddenly the whole thing just breaks open. It's like the straw that broke the camel's back. Do you know the story? What? No? আচ্ছা, তার দরকার নেই। এরকম story না। It's a life lesson. So এটা আমি দিব না। Yeah, 238 has magic number in it. Remember magic numbers? So it actually has a magic number which allows it to be a bit more stable than 235 in fact. So 238 কিন্তু হচ্ছে nature সবচেয়ে easily পাওয়া যায়। Magic number জানো না? Well, what's the magic number? Who can tell me what's the magic number? That's actually very close. Magic number হচ্ছে in the nucleus we have protons and neutrons. If you have too much proton, it's a problem because what's too much? Repulsion. If you have too much neutron, that's also a problem because too little attraction is the neutrons and neutrons can't stick together. So there's actually a combination of protons and neutrons that make the structure the most stable. Those numbers are called the magic numbers. So there's 4, 8, 28, 56, 128. These are the numbers out there. So if you can combine these combinations, right, and you have a nucleus that has, let's say, 28, 56, and 128, that nucleus is going to be more stable than its peers because whatever magic number takes this for it. So 235, in theory, should be more stable than 238. Currently, it's too smaller, but 238 has a magic number in it. Doesn't know what is it? A bit more stable, but both of them are very unstable. So at the end of the day, they will decay and do things. So this is called the chain reaction, which is highly unstable. It breaks into krypton and barium. It can break into xenon and boron. A lot of combinations out there. But interestingly, it releases what? 3 neutrons. So in neutrons will a future key reaction help for it. Chain reaction, and that's how the chain reaction works. But again, এটা আসার chance remote. আমি just করে রাখলাম because this was in your O levels, so এখন exist করে, so জেনে রাখলে ভালো. I don't see the point of adding fission and fusion in your syllabus but not going into this. আমি বইতেও পাই নাই, syllabus mention করা নাই, but just to be safe I haven't given this. Okay, so what are you supposed to know though? Define nuclear fission. Nuclear fission is the process by which a large unstable nucleus splits into smaller, more stable nuclei with the release of what? Energy. One common theme for both of them is that whatever they do, what do? Release energy. And why is that so? Because I think I told you this idea that the more stable a system becomes, it starts to shed off energy, or it's more stable than it can be, right? So energy ছেড়ে দেয়. So whenever you try to attain stability, it starts to release what? Energy. And that's what fuels the star. কারণ সানের পরে কি হয় প্রথমে? Hydrogen fuse হয়, তারপর কি ফর্ম হয়? Helium. Do you know that the helium will again fuse? And helium fuse করে beryllium হবে, carbon হবে, nitrogen হবে, oxygen হবে, silicon হবে. এরকম করতে করতে একটা পয়েন্টে what will start to form? Iron. But once iron forms, right? Iron are the most stable. Does it have any reason to fuse? No, that's when the star dies. Because there's no more what available. Energy to keep the mass out, the radiation pressure. Yes and no. So when a star dies, it's usually very violent. So if it's a supernova, the iron is just thrown out into space. So it gets white dwarfs are iron. So white dwarfs are just balls of iron left behind the core. But there's a catch though. Not all stars actually fuse iron and die. They die earlier, like our sun. Our sun previously died before iron started forming into it. It's the stage 1 cycle where you form a planetary nebula. So এটা core iron ছিল না. So iron formation হচ্ছে supernova গুলোতে হয়, like the type 2 stars, the red giants and the supergiants. So ওইটার মধ্যে iron form হলে it collapses upon itself. It's a mystery. So there are many theories out there, but we know one thing for sure: the sun actually came back. Because the thing is that there are planets around the sun, right? And the planets have elements that are very mature. Like, Earth, the key element abundant. What's the most common element on Earth? Silicon. Silicon is the most. So people think it's nitrogen or oxygen or something. No, it's silicon. Silicon is like 99.9% the Earth's crust, like soil. Okay. Those are also a mixture of silicate. So they're still silicon, but they're like liquid form. The very thin layer at the top, right? Oita key. Nitrogen. So take a basketball, put the basketball in water, take the basketball out, ওই উপরে যে water filmটা থাকবে, that's actually our atmosphere. That's where we live, by the way. That's the entire basketball is the Earth. We have no clue what's inside it. But we have some idea there's molten magma, lava, and everything. But we live in 0.1% of the Earth's entire volume, the crust. It's made up of silicon, and the gas is made up of nitrogen, which is 78%, and a small amount of oxygen, which is 22%, right? Elements below, silicon, nitrogen, and oxygen can only come from a star that was what star? A mature star, where a lot of fusion was going on. So the question is, where did these elements come from, right? So we now believe that our sun in the previous past life of its, right, it actually underwent an explosion, like a supernova, planetary nebula, where it spewed out all the gases. But whatever reason, it again brought back some of the gases in and became a what again? New star. But some of the masses got what outside? Stuck outside. Those masses eventually became what? Planets. And that's how planets form, by the way. Planet formation is ushered from the residual mass out there. So our sun, that's why we know our sun had a rebirth. But the confusion is that why did it do this rebirth? Mass there are a lot of theories out there. The most common one out there is that that explosive nature wasn't explosive enough to kill it out. Our theory, the controversial one, is that our sun came from another part of the galaxy. It was strained out and then it got stuck in this part. So it came from a much more mature location. We can take it picked up masses. Okay. Right. So this is fission and fusion. Do you guys have any question? I'll show you some animations now. But from a question, yes. How does? Oh, so deuterium is when the hydrogen nucleus gains a neutron. So let's say there's a nucleus out there, proton, and the neutron is going by. And let's say the neutron comes and sticks to it. Wouldn't the proton and neutron bind together? That's when it forms. Is it needed though? No, it's not. That's why deuterium is what compared to hydrogen? Unstable. Okay, so the presence of neutron makes it unnecessary. Doesn't it's little unstable. Okay, let's look into this. আজকে আমাদের হচ্ছে main agenda হবে হচ্ছে to start radioactive decay. 4 equations হলে radioactive decay হয়ে যাবে আমাদের. ওই যে নিউক্লিয়ার রিঅ্যাক্টর যেটা মডারেটরস কন্ট্রোল রডস না ওটা Okay, I'll show you a few things here before we start the topics. We're done with the first part, nuclear stability. Okay. Just uranium ki fission undergo or other elements can also. Yeah, plutonium, polonium, they're also very famous for it. Okay.
Nuclei of certain heavy nuclei.
Right. So right now this is a nucleus here, and it is unstable because the ratio of protons and neutrons are not the right number. So it's trying to get rid of something, right? So what it does is that
just plutonium or uranium.
At a point, it just splits up like that and releases energy in it. But actually, do you guys remember what was the energy released from a nuclear fission reaction? Nuclear fission যখন হয়, the energy that's released, right? What form is it? O-level question. Radiation মানে waves. It's a common mistake. When nuclear fission takes place, what is the energy release? Heat energy to exist করে না. What was it? Yeah, it's actually the kinetic energy of the particles produced. এই যে এখানে যখন explosive একটা জিনিস হয়, the nuclei that's released, right? The both of them, they fly off. They fly off with what? K. And that K is the energy that's released. That's fission. Fusion, that's true. Radiation produced by fusion. There's actually electromagnetic gamma radiation coming out from it. But I'll show you right now. So we fission, we just put water around it, and the water absorbs this energy. And what does the water start to do? Boil. And we put in a nuclear reactor. Fusion, you have to use that radiation and heat water using it. Okay, so that is only there. This is the only fusion reactor we have ever built. It out France, France with Germany. Recently all our prototypes, but this one was built quite some time back. This was based on a very famous theory paper. Earth fusion kora lage, this is how you do it. So it works, but it's not stable. It lasts for I think 10 milliseconds. So bondo keno hoye jay? It's because you don't have enough what? Particles, deuterium to sustain it. Fuel nai amader. Okay? So yes. The hydrogen is the easiest. So helium, beryllium will require even more extreme temperature. Like even sometimes stars can do it. Like the sun can't fuse heavy elements. But for that you need like a red supergiant. Okay. Yes. On করব So this is actually what's happening there. There are particles moving at very high velocity. They're colliding, and every time they collide, they fuse together. And what do they release in the process? Energy. So this is happening now. এখানে যদি notice করো, not enough is going on right now. Ekta, duita, like barely colliding, right? We want the number of successful impacts to be what every second? Very high, so that it can produce its own energy out there. Okay. So surprisingly, the most successful fusion reaction ever done was done in a bomb. Yeah, it's the biggest bomb ever made. It's called the Tsar Bomba. It's a hydrogen bomb. So the physicists who came up with this bomb, they just lost their mind. I'm বলি কি করছে? So they saw the nuclear bomb of Hiroshima Nagasaki, right? ওটা কি bomb? ওটা হচ্ছে nuclear fission reaction, which is uranium থেকে, and ওটার energy is insane, no doubt about that. Okay, it flattened two cities. The Russians thought we'll use the energy of a nuclear bomb to start another bomb, and that's what they built. So they built something called a hydrogen bomb, যেটা nuclear fusion করে energy release করে. But fusion এর জন্য temperature কি দরকার? Very high. So what they did was they used a normal bomb, uranium bomb. We'll call it the normal bomb. They used a uranium bomb to set off a reaction. But uranium bomb থেকে যে energy release করছে, that started and fueled the what process? The fusion of the hydrogen, and that produced the biggest bomb ever made. It's called the Tsar Bomba. Okay, so I mean, there's no comparison to it. I can tell you it's destructive, right? But it is so big, it's mushroom cloud, right? It goes into stratosphere. Oh, it's a comparative chart. Oh, they did it. They did it in Siberia. Siberia, there are some desolate areas. Yeah, they just blew up. They do it underwater, so the water rises up, right? And or they do this in the space, not on the ground. Ground can trigger earthquakes. Yeah. So. Really? কি হয়ে যাওয়ার কথা? কি হয়ে যাবে? ও হ্যাঁ হয়তো, but yeah, the Siberia সব জায়গাগুলোতে they do this. এই যে so yeah, these are the ones out there. Hiroshima Nagasaki তুমি দেখো, it's called a little boy. ওই যে শুরুতে যেটা, okay? So do you see Mount Everest? Mount Everest is, 8 kilometers up in the air. Plane যেখানে উড়ে, ওই জায়গাটা is Mount Everest, okay? So when you're in a plane, that's the height of Mount Everest. Very similar. The Tsar Bomba goes up 95 kilometers. The cloud, the plume. Yeah, it's into outer space. Satellites এর সাথে বাড়ি খায়, মানে ওরকম লেভেলে চলে যায়, okay? So yeah, they tested in 1961, and number যদি দেখো তাহলে একটু better বুঝবা. The Hiroshima Nagasaki bomb was 15 kiloton, right? And look at this one, Tsar Bomba, 50,000. Okay, but it's even nightmares can't make this up. It's actually just insane. Oh, they have a collection of these. Yeah. So they definitely will have. যদি এরকম success হয়, why would they stop with one? Yeah, they just got rid of the little man. Or fat boy, or fat man and little boy. Yeah, the big ones are still there. Definitely, way more. In terms of energy efficiency, it outweighs it. কারণ হচ্ছে fusion-এর মধ্যে যেটা হয়, most of the mass retains. Fusion-এর মধ্যে the masses keep joining up, and there are small particles out there, you can pack more into one place. But আমি তোমাকে যদি হচ্ছে handful of hydrogen দেই, like that, and handful of uranium they like that, you'll have more hydrogen here because hydrogen molecules are what size? Smaller, so you can pack in more particles here. Combined nuclear reactors, right? The problem is that it's a good thought, but the first reactor has to be a bomb, because normal reactor it doesn't temperature rise on it, so the temperature 10,000 degrees Celsius rise. Bomb যদি explode হয়, all that energy is released in a split second. তখন the temperature reaches like million degrees Celsius, which then can help your fusion process. So normal reactor মধ্যে temperature তো বেশি হয় না. Yeah, we just want to boil water, right? That's what we do in normal reactors. So ওইটাতে হবে না. Which one? Carbide. Okay, let's finish this. I mean, just art animation দেখাইনি, and then we'll be done. Okay, to show my screen, let's look at the different types of reaction out there. It's called nuclear fusion. We already have the deuterium here and tritium. See what happens, okay? So দুইটা এসে collide করবে, and do you see that red thing came out? That's basically radiation. Okay, I'll repeat this again. That's the radiation released in the process. Okay, that's your gamma radiation. আর এটা হচ্ছে the nuclear fission where 235 is unstable, but it is not very unstable, so we'll trigger it by adding a what to it? Neutron, and then it becomes very unstable, and then it throws out the particles. Those particles have a lot of K, we harness that K. Okay, so we're done with our nuclear fission fusion part. A chapter we last class I just wanted to wrap up whatever was pending. এখন হচ্ছে we'll start the next part of our topic, probably the last proper theory that you have in your syllabus. এটা হচ্ছে radioactive decay. So this will be a throwback to what you did in your O levels. Radioactive decay যেটা ছিল ওইটা, we'll just build on it. Okay, so পুরো জিনিসটা বুঝাবো, এখানে লেখার কিছু নাই। I'll derive 4 equations at the end, ওই 4 equations তোমাদের খালি হচ্ছে মনে রাখতে হবে। তো সবাই একটু স্ক্রিনে দেখো radioactive decay one last time. Clean bomb. হ্যাঁ, এটার বাই প্রোডাক্টে কোনো রেডিয়েশন নাই, মানে রেডিওঅ্যাক্টিভ এলিমেন্টস নাই। No, I don't think so. But কিছু হলেই তো রাশিয়া বলে we are moving it right now. কিছুদিন আগে হচ্ছে I think they got a little scared of Ukrainian missiles and drones. তো বলছে ওরা বমটাকে হচ্ছে আরেকটা জায়গায় নিয়ে যাচ্ছে, and ওটা শুনে everyone like settles down. Yeah, just the fact that they took it out of the hangar and took it somewhere else, right? Everyone's like quiet now. Yeah, it does. It's a very small amount, but instantly the fusion produces so much energy, it vaporizes those elements. So we exist করতে পারে না, মানে just turns them into ashes. হ্যাঁ, এই যে বললাম তো এই রুমে হলো। হ্যাঁ, হতে পারে, just randomly there are two particles moving randomly, they have very high energy, they collide randomly at very high velocity, the required velocity, and they fuse together and they produce energy that is 1 into 10 to the power minus 19 joules. So yeah, so it doesn't really do anything. That's why I'm bolchi to the fusion is not important. What's important? Density, so that you have enough of them being generated. Okay, let's start. Shall I screen it? I have this electronic balance here. It's a new topic. Okay, it's not the one we did. I did to separate. I have this electronic balance here, and on top of the electronic balance, I'm going to place a lump of uranium. So uranium is famous for having this orange yellow color. The actual uranium lump the way the color থাকে. And I'm going to use a very particular mass here, 235 grams of uranium 235. The reason I'm using this number is so that you know how many particles are here. So this is 235 grams of uranium 235. What does that mean? 1 mole, right? So this is 235 grams of uranium 235. So that means in this particular sample, how many uranium atoms are there? 6.023 into 10 to the power 23 atoms. Each atom of uranium is highly what? Unstable. Okay, so এখানে প্রত্যেকটা atom হচ্ছে খুবই unstable. Now to become stable, what does uranium do? So uranium হচ্ছে to attain stability undergoes something known as a radioactive decay. So 235 and 92, you'll find the balance between proton and neutron doesn't exist here. Proton number 92, neutron number 143, like really far away. It's unstable. So what it does is that it releases a particle to become stable, and it releases a particle that's stable itself as well. What is it? An alpha particle. Remember alpha particle from your O levels? So we alpha particle release করে, and alpha particle হচ্ছে তোমার 4 and 2 হয়, and as a consequence it produces a byproduct here. It's called thorium. So thorium আমাকে একটু বলবো composition কি হবে? Yeah, 231 and 90. Thorium has a different color. It's a different element. It has different color, different texture, different everything, right? So right now I have uranium on the table, and the uranium is unstable, and the uranium is supposed to decay and form what? Thorium, right? Can you tell me what will you observe? Thorium, by the way, is green color. Will you observe that suddenly all the uranium just turn into thorium, or will it be a little different? Yes. So যেটা observe করি আমরা is that when you look at the sample here, thorium form হওয়া start হয়, but কোথায় হচ্ছে? Randomly, different places এরকম করে, and slowly but surely the whole thing will eventually become what color? Green. But does it all happen at once? No. Why? Because we realize that this process of decay has two words that perfectly describe it: random and spontaneous. So whenever you have a nucleus, let's say I have a uranium nucleus in my hand right now, and it's unstable. How can I make it decay? What do I do to make it undergo radioactive decay? কি করতে পারি? না, fission না, just normal alpha particle decay যেটা, ওটা কেমনে induce করতে পারি? You can't. It is impossible. We have no way to make an unstable nucleus decay. So when you have the sample in your hand, right, the uranium, one single atom, it can decay any moment, and that any moment could be for uranium anywhere between 1 second and 230 million years. It 230 million years randomly extreme can remain what as well? Stable. Okay, so this process is entirely random. Also spontaneous. Spontaneous মানে হচ্ছে I can't really do anything to make it happen faster, but I can't influence it. So আমি টেম্পারেচার বাড়াই দিলে হবে না, প্রেসার বাড়াই দিলে হবে না, লাইট দিলে হবে না, ক্যাটালিস্ট দিলে হবে না. It is just completely out of our control. That is what radioactive decay is. There's nothing you can do about it. It will only happen on its own. It uses probability. So there's a probability that it follows for the decay. যদি high probability হয় of decay, that sample is very radioactive. মানে খুব rapidly decay হয়ে যাচ্ছে. আর low probability হলে it's going to take what time? Very long time. But despite knowing the probability, as it's with probability, you can't predict exactly কখন হবে, because it's eventually a what? Chance. বুঝছো জিনিসটা? So I'll show you more details about it. You had a question? Fission is when the nucleus splits into two pieces, bigger, like smaller nuclei. The uranium is just releasing one small particle out there. The energy release here is not much. Okay, so that's why this doesn't fuel nuclear reactor. Okay, so to দেখো screen এ, so somebody decided যে আচ্ছা uranium তো form হচ্ছে, মানে thorium এ convert হচ্ছে, let's plot a graph here. A graph for the activity মানে কতগুলো alpha particle বের হচ্ছে. And when we plotted the graph for activity, which is by the way measured in what unit? Becquerel. Do you know Becquerel? Do you know CPM, counts per minute? তো all ছিল। আচ্ছা, না জানলে problem নাই. Becquerel, BQ, is the unit for activity. How many particles to release every second? Okay, and x-axis হচ্ছে time. এই গ্রাফটা দেখো, খুবই important. When we plot the graph for activity, the graph looks something like this. খুবই jagged একটা এরকম random looking graph out there. What does the graph tell us? That the process is random. Just look at this. This is all over the place like that. Now this is for uranium. Somebody decided, let's try this for another element, and they found it was also very what? Random. So radioactive decay is random. They tried to increase the temperature. It didn't really affect it. It still did the same thing, which means it's also what? Spontaneous. So that's how the decay looked like. It was like very jagged like that. But then they thought, let's try to smoothen out the graph. I mean, there's a lot of chaos going on there, but let's try to smoothen this. Smoothen মানে হচ্ছে, let's get rid of those rough edges. And তখন we found something unique. We found that all these radioactive graphs that look very random actually have a very similar pattern to their process, which means that despite them being random, within the randomness, there's actually what? A system to it. Do you look at the three graphs here? If I ask you, are these three graphs similar? You probably think so. There's a pattern to it. It's very steep at the start. It flattens at the bottom. If it was truly random, would you see this? No, right? So that's when we realized that, yes, maybe we can't predict what. When does the particle decay? Which particle decays? But we can predict overall what happens. Now, এটা বুঝার জন্য অনেকে একটু confusion হয়, so I'll give you an analogy, okay? এই chapter অনেকগুলো analogy দিব, so bear with me. First one হচ্ছে the analogy of this. So screen it to দেখো. I have a container here and it contains coins, unbiased coins. একটু probability use করতে হবে chapter, so probability যদি জানো তো ভালো. Do you have probability in your A levels? Statistics. Do you understand the statement I'm going to make right now without replacement? That's to be like that. So yeah, I have these coins in this container. Coin, and coin probability of a head or a tail is 50%, half. And it's an unbiased coin. Add within the coin, there's a red coin out there. Baki coin is a normal coin. What I'm going to do right now, I'll take this, I'll shuffle, and I'll toss all the coin on the table. If there are 100 coins here, can you tell me how many heads will you get? 50. And how many tails? 50. Let's consider যেগুলা head show করে, they're decayed. So আমার হচ্ছে 100 থেকে কতগুলো coin বাকি থাকবে তাহলে 50. আমি 50 গুলো আবার দিলাম. I shake them and I toss them again. Well, how many do I have left? 25. তারপর হবে, let's say 12. তারপর হবে 6. তারপর 3. তারপর maybe 1. And then all of them decay, right? Can you tell me which process, which turn produced the red coins decay? মানে কখন red coinটা বের হয়ে গেছিল? Can you tell me which one? Is it the first one, the second one, the third one? Which one? Sorry? It could be any one of them. It could be, if the red coin is lucky, the last coin it stays. It is possible because there's a it's called a statistical bias. Just don't get if you were that coin, right? You think luck is everything. কারণ হচ্ছে প্রত্যেকটার মধ্যে you survive, right? But do you understand the probability of that for happening? So in any container, there is always a coin that is what? Astronomically lucky. It has to be that, right? Because survive courses so many tosses. But that's why sometimes people who get lucky, they think that's how it is. But you're just part of the process. Okay, it just ended with you. So anyways, kon chancer moddhe hocche do you think was the red coin out? We can't say, right? But isn't it true that we can predict এরকম turns লাগবে? মানে আমার হচ্ছে কয়টা চান্স লাগছে 1 2 3 4 5 6, right? এই এক্সপেরিমেন্ট যদি 100 times করি, তারপর more or less প্রত্যেকবার কয়বার লাগবে for all of them to go away? 6 times. So what is predictable? The bigger picture, like the total time taken, the total number of turns taken. What is not predictable? Individual behavior. So when it comes to radioactivity, echono, we can't predict when a nucleus will decay. We can't predict which one will decay, when will it decay, how will it decay. But we can predict one thing though, that over a certain amount of time, these many will decay. And that's what we're gonna learn. Okay, because if everything was random and unpredictable and spontaneous, right? But there's actually a method here, there's actually a model that we can generate. Are you clear with this? Okay, this is one analogy out there. Art analogy হচ্ছে the popcorn analogy. এটা সবাই বুঝে না, তার জন্য আমি এটা পরে করাই. But it was there in a past paper. তোমাদের না Excel এ দেখো তো বুঝো নাকি? So the popcorn analogy টা অনেকে বুঝে না because the system they use is little maybe not everyone's accustomed to it. It's a microwave of popcorn. Do you know what a microwave popcorn is? So it's this packet you can find. ওই প্যাকেটটা seal করা থাকে. There are corn kernels inside it. You put it in the microwave oven. You put 2 minutes in it. তারপর কি হয়? It pops and becomes popcorn, right? So let's say I take one of these packets out there. There are lots of these corn kernels inside it, right? And amongst them, there's one red one colored, red curriculum. I put it in the microwave oven. I turn on my microwave oven, right? Try to imagine how it sounds. So যখন pop করা start হয়, right? Pop করার soundটা, the frequency কখন বেশি? শুরুতে না শেষে? Yeah, না শুরুতে is like popping all over the place, right? Over time, the bastas it dies out, like 1 2 3 4, because shurute there are more particles available, more of them can decay. Over time it starts to slow down, and eventually at a point it's silent because all of them have decayed. That graph for sound of popping follows the same of a radioactive decay. It is the same graph out there. And can you tell me, without seeing it, right, just by hearing it, which one was the red one? No, right? But isn't it possible to predict that the red one will have decayed sometime? So that's what we can do. We can predict 2 minutes or more that the red has gone, but we can't say when it happened. Okay, so analogy there, how is it random? give evidence of it. We can't predict when it happens, which one happens, how is it spontaneous, or is it spontaneous? So I found this question a little unfair at Excel problem there. The spontaneity is not there. You can actually make the popcorn pop faster. There's a way. You can put salt on it, it conducts better. You can increase the power of your microwave oven, power option. So can I make it pop faster? Yes. So is it spontaneous? No. So is this a proper demonstration of radioactive decay? Randomness, yes. Spontaneity, no, because it is not spontaneous. You can actually influence this. Okay. Right. So that's the radioactive decay introduction. I'm going to do something. It's a calculator ready. I'm going to do some math. Okay, সবাই একটু স্ক্রিনে pay attention here. This is our A2 starting here. So far যা করাছি, those are all our stuff. A2 তে হচ্ছে কি করতে হবে? So we need to come up with equations to model this behavior. কেমনে করি দেখো? So we will play a game here. That's how we actually model it. It's not my thing, it's how it's actually done. Do you know these things in the fair places where it picks up the toy? Yeah, those claw machines, right? It's a claw machine here, okay? And a container ভিতরে there are a lot of spheres here. অনেকগুলো বল রাখা এখানে। আমরা যেটা করব is we'll try to take the ball out using the claw machine, okay? তখন দেখবা it actually forms a model for radioactive decay. I'm going to show you right now কি হয়। So এই যে এখানে হচ্ছে অনেকগুলো বল রাখছি ভিতরে। It's going to be a mathematical model here, okay? So সবাই স্ক্রিনে দেখো। Right now in this container you have 50 white color balls here, and a crane jetta it comes down and it'll pick up your spheres here with a probability of 1/10. মানে কি? মানে হচ্ছে, is it possible for this claw machine to pick up all the spheres? No. So যতগুলো sphere থাকে, it is always successful in picking up how much of it? 1/10. 1/10 is the probability. তোমরা কি বুঝছো? Sorry. Why 10? Oh, it's just how this is. Let's say there's a container of rice and you put your hand in and you scoop out the rice, right? Are you going to take all of them out? No. So how many of the total do you scoop out every time? A certain proportion? That is that. That would mean you're just picking up one. This can pick up more. You can pick up more than one. আচ্ছা, তোমরা কি বুঝছো 1/10 মানে কি? মানে আমি যদি এখন দেই, কয়টা আসার চান্স? Yeah, that's what I'm trying to say. Okay. Now, something important, this scooping process is our radioactive decay. Okay. When our radioactive decay process, that's the scooping process. And ball gulo hocche your atoms. Now, let's start the process. Okay. Let's start with the first one. Oh, by the way, I'll just keep one here, different color for explanation purpose. If I scoop here, can you tell me how many will come out from this? মানে কয়টা বের হবে? 6. How 6? 6 বলছিল? Oh, 5. হ্যাঁ। So এই প্রসেসের মধ্যে how many balls will be released here? 5. So 5 হচ্ছে removed, and this is without replacement. তার মানে আমার এখন এখানে নাম্বারটা কমে যাবে। কয়টা বাকি? Very good, 45. So we'll repeat this process. I need your help with each step. Can you tell me if the probability is still 1/10, right? What is the number of balls that will be removed now? 4.5. I'm gonna round up to make our process faster. So let's say 5টাই বের হলো। আবার যদি এই প্রসেসটা করি, how many will be released? এখন তো এটা কমে যাবে, 45 থাকবে না, কত থাকবে? 40. তোমরা কি বুঝতেছো what I'm doing here? আচ্ছা, এবার কয়টা বের হবে? Definitely 4, right? So 4 বের হয়ে যাবে। So এটা 4 বের হয়ে যাবে এখানে। So this is going to be 4. And if I continue to do this thing, right, over time, the number of spheres in the container কি করতে থাকবে? কমতে থাকবে, right? So let's try to do this quicker. পরেরটা কত হবে? ওই যে 40 তো 40 থেকে 4 চলে গেলে কি 36 থাকবে না? So you have 36 here. So how many will be released here? Again 3.6. Let's just round it up to 4. তারপর আবার যদি চলে যায় 32 আসবে। 32 থেকে যদি 10% নাও তাহলে কত থাকবে? 3. সেরকম করতে করতে একটা পয়েন্টে কি নোটিস করবা যে এটা কমে হচ্ছে লেটস সে 3, রাইট? সো 29 হয়ে গেল। আর এখানে হচ্ছে এটা কত হয়ে যাবে? 3 or 2. So let me explain how is this an analogy of radioactive decay, okay? So screen একটু দেখো, পুরো স্ক্রিনটা দেখাই। 1/10 টা হচ্ছে whenever you have a scoop going of the total spheres available, what fraction can it pick up? 10 of them, মানে 1/10 of whatever is there. So যদি 100টা বল থাকতো, the scoop could go in and take out how many? 10. যদি 1000 থাকতো, 100. So it's basically the chance of picking it up. Okay, so I screen it. Let me explain what the main part here. So how is this related to radioactive decay? So this thing, the number of balls that are removed every cycle, what would that be a representation of? So that is the representation of activity. Activity হচ্ছে the number of what release every second from a nucleus, particles, ওই যে alpha particle যে বের হচ্ছে না? So these removal represents the activity. Can you tell me activity কি same থাকে না কমে যাচ্ছে? কমে যাচ্ছে কেন? It's a very important question. Right, very good. So over time, the number of unstable nuclei কমে যাচ্ছে না? So our chances of radioactive decay কি হয়ে যাবে? কমে যাবে? Do you understand? Because আমার প্রথমে যদি 100টা বল থাকতো তাহলে 10টা বের হতো। এখন যদি 10টা বল থাকে কয়টা বের হবে? একটা। So that's why whenever you have a radioactive sample, over time, what happens to its activity? Decreases. কেন? Because over time, the number of unstable nuclei available is decreasing. That's activity, right? Radioactive decay মধ্যে এই নাম্বারটা তোমরা কোনদিন শুনো নাই, I mean স্কুলে করে থাকলে শুনে থাকতে পারো, but this is O levels এ ছিল না। This is actually what governs radioactive decay, and we haven't learned this in O levels. Let me introduce this fraction. This is called the decay constant. A decay constant is the reason behind half-life, the rate of decay, সবকিছু. It is represented by the symbol lambda. This number is all that you need for our syllabus. A2 te a number to dictates what? The way radioactive decay takes place. And very interestingly, a number is fixed for an element perpetually, for eternity. So uranium that was formed at the Big Bang, let's say, but let's talk to the decay constant. It's going to be the same for the rest of the universe's lifespan. It can never change. It's based on the structure of uranium. So uranium's probability of decay will always be what? Same. এটাকে ইনফ্লুয়েন্স করতে পারবে না, এটাকে ম্যানিপুলেট করতে পারবে না, এটাকে কোনোভাবে চেঞ্জ করা যায় না। That's the reason why when uranium decays, it decays as it decays. There's no way you can manipulate this, okay? And this is the one that we didn't have in our O levels. এখন A levels will work with this thing. It's called the decay constant. And this represents the number of particles you have. And this process is a radioactive decay. So let me show you radioactive decay one more time, okay? I have container here. I put my hand inside. I take some particles out. These are decayed. I go back in. Do I have more or less particles now? So the ones that come out, less hobe. So over time, as I'm taking particles out, right, isn't the fraction of particles that come out getting less and less? That particles that are getting out are known as the what in your radioactive decay activity. Okay, মানে কতগুলো particle আসছে। So আমার যদি the pool of particle is decreasing, within the number of particles coming out also decrease. So that's why when our samples number of unstable nuclei decreases, what also decreases? The radiation, the activity. Okay, আরেকটা জিনিস হচ্ছে activity hamper করতে পারে। What is it? The decay constant. Imagine the decay constant here was 1/1000. Wouldn't that mean that this is going to be a very slow process? মানে দেখা যাবে বারবার ক্লক করতেছে, কিছুই আসতেছে না, 1000-এর মধ্যে একবার একটা বল চলে আসছে। Wouldn't this take an awfully long time to decay? Example হচ্ছে, let's say, granite. Granite has a half-life of 2 billion years. মানে গ্রানাইটের হচ্ছে half life is so slow. If I give you a sample of granite, right, in a 100,000 years, একটা particle বের হয়. Is it very active? No, right? Its activity can be measured, but I'm also very curious. I don't know how. Like, how did they even figure out it was radioactive? But the fact that its activity is extremely small, because its lambda is what? Very, very small, 10 to the power minus 28 or something. Okay. So yeah, এগুলা নিয়ে আমরা এখন next class will form equations.